Hi everyone, my name is Barry from Barry Science Lab, and today we're going to be doing Lecture 2 of Complex Analysis. Now, remember what we did last time. Last time we just got introduced to the basics of complex analysis, including the fact that you can graph it on a plane. And this treatment of complex numbers is so good that we're basically going to be treating the complex numbers like R2 for the rest of the series. Of course, there are going to be some things different, but many visualizations that we can make are the same. So, remember what real analysis was about. We completely defined what calculus means on the real numbers. We define what limits are, what integrals are, what derivatives are, what continuity means, what smoothness means, what sequence convergence means, etc. And the convergence of series means. And in a similar way, in complex analysis, we're going to define what calculus on the complex numbers means. And the most glaring way this comes up is in the series for cos x, sin x, and e to the ix. So this is the biggest use of complex analysis to justify one of the most important equations in math and physics. It allows us to say that sequences in the complex numbers can actually converge, which we don't have a notion for that yet. So, what does it mean for what does it mean for things to converge in complex numbers? What do limits mean? What do derivatives mean? What does analyticalness mean? And so many other things. That's what complex analysis is about. And today, we're going to be looking over limits and sets. So we're going to start with limits. Now, what is a limit? Well, recall that we defined limits of a sequence in real analysis. We defined a sequence xn as approaching L if, and only if, for any epsilon, there existed some natural number n greater, there existed some natural number n such that if k was greater than n, the distance between xn and the limit was less than epsilon. What does this intuitively mean? Well, it means that let's draw what a typical convergent series might look like. Sequence. We start here, 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 and it eventually centers on this being the limit. So 1, 2, 3, 4, 5, 6, 7, and so on. Now, you will notice that, of course, it gets arbitrarily close to the limit as time goes on. If it doesn't get arbitrarily close, it's not a limit, because then you could zoom in and see that, after all, if it goes something like, here's the limit, and there's some epsilon bubble beyond which you can't get arbitrarily close, then there's nothing converging to that limit. It's converging to the outer portions of that epsilon circle. It needs to be able to get arbitrarily close, or otherwise there's going to be this weird discontinuity here. It's not going to be approaching L, it's going to be approaching this bubble that's right outside L. So the arbitrarily close requirement ensures that any sequence that's approaching a number will actually approach it. So it means that given any distance that we require, there exists a number high enough such that the distance between that number when plugged in as the index and the limit that we want is sufficiently low. So in other words, we can find an index high enough for any distance we require such that that distance comes closer and closer and closer to L. Now, in complex numbers, we want mostly the same thing. It's even the same symbol. We want the distance from Zn to L to be less than epsilon. I mean, basically, all you have to do is replace these symbols. Even that's just stylistic. Now, this also holds for functions. Actually, what's more interesting to talk about is sets, because we're really going to need them in complex numbers. In real numbers, you might recall the Bolzano-Weierstrass theorem. What does this theorem tell us? Well, it tells us that if any sequence or set that we have is bounded, which means that I can't recall the formal definition. Which means that the difference between its infimum and its supremum exists. Of course, if this is pretty intuitive because if a sequence was not bounded, there would be no supremum or infimum. So, if a sequence is bounded, this tells us that any subsequence within it, if a set is bounded, then any sequence within it, if that sequence approaches a limit, if a set is bounded, there is going to be a sequence in it that obtains a limit, okay? And similarly, if a sequence is bounded, there is a subsequence of it that will obtain a limit. There we go. Now, where do complex numbers come into play? Well, compactness is going to be a lot more important in complex analysis than real analysis. One of the many properties that compact sets have is that any complex function, f of z, will always obtain some maximum if it's evaluated over any complex set. You can always find a point at which it obtains a maximum value if it's within a compact set. We'll prove that next time. This time, we'll just say what it means to be compact. Now define accumulation points. Accumulation points are just points where the sequence accumulates. As in, a point P is defined to be an accumulation point if there are infinitely many n such that P minus Zn is less than epsilon for any epsilon greater than 0. So in other words, if some subsequence of the sequence gets arbitrarily close to it, or in other words, if some subsequence of the sequence has it as a limit. That's right. So that means that any bounded sequence is going to have an accumulation point by the Bolzano-Weierstrass theorem because it's going to have a subsequence that converges to that accumulation point. And in a similar way, any set that is bounded is going to contain infinitely many accumulation points. So, well, actually no. Any set that is bounded will, well, not infinitely many, But for every single sequence that can possibly be formed by elements in the set, if that set is bounded, then it's going to contain all of those accumulation points. Now we redefine a compact set to be a set that contains all accumulation points of any sequence Zn formed such that Zn is inside the set. Okay, so now we're going to prove that it's equivalent to being closed and bounded. And remember, to prove equality, you have to prove things two ways. So first, we assume that our set is compact and wish to prove that it's closed and bounded. Now, if our set is compact, that means it contains every single one of the accumulation points of the sequences within. Now, what does that mean? Well, accumulation points, some of them are going to be limit points. Note how I said not all of them, especially because any non-convergent sequence can still have accumulation points, but they're not going to be limit points. So some of the accumulation points are going to be limit points, but all limit points are accumulation points. It's like the squares rectangle situation. Think about it for a second. And so that means that if a set contains all of its accumulation points, it's naturally going to contain all of its limit points, which crosses off the closed requirement. Then we have to make sure it's bounded. And, accumulation points. Oh, wait, what? I have to work out this part. Okay, let's try to imagine a set that is closed, but it's not bounded, and yet it contains all its accumulation points. But wait, this is where the Bolzano-Weierstrass theorem comes into play, because it says that any bounded set will have accumulation points within it. But we can't say that if our set is not bounded. There might be some sequences that don't have accumulation points at all. And so that means if a set is such that every sequence within it has accumulation points that are contained within it, then it has to be bounded as well by the Bolzano-Weierstrass theorem. Now we have to prove it the other way around. Closed and bounded sets are always compact. Well, that one's pretty easy because if it's closed, it contains all its limit points. And if it contains all its limit points, it's going to contain all its accumulation points as well. And, if it's bounded, then that makes it, well, actually, let me think for a second. Oh, yeah. Yeah. Like, no set can contain infinity. It's not a number. So, any non-bounded set can very easily have a sequence that diverges to infinity, but infinity is not going to be in that set. Which means that if our set being bounded is the only way it can be compact, which means that we've proved equality both ways. So any set that is compact is also closed and bounded. That's it. Thank you everybody for watching, and we'll see you next time where we discuss some properties of compact sets.